Now let's talk about uh, the counter that's made of a semiconductor, and what we call those counters, we call them as semiconductor radiation counters, and and the working of a semiconductor uh, detector is basically based upon the properties of p-n junction. So we have a p-n junction, say P and N, and we have a situation like this. Now, a p-n junction diode, what it does, it consists of p-type semiconductor that's in contact with the layer of n-type semiconductor. The conduction in the n-type semiconductor takes place through the motion of electrons. And in the p-type semiconductor, uh, uh, what we have, the current we have is through the motion of holes in valence band that behave like positively charged entities. Now, at a p-n junction, the free electrons that are present in n-type, they get diffused across the boundary into the p-type, thus leaving free electrons, thus leaving the n-type material positively charged. As p-type material gains the electrons, it starts gaining the electrons, it acquires an equal negative charge. Now, the diffusion of electrons continues as we understand it from the very fundamental point of view, that this diffusion of electrons continues, and the filling of the holes in the p-type gives rise to more holes in n-type. And this action amounts to as if the holes have actually been diffused across the boundary. And the process of diffusion continues till we have a state of equilibrium. And once an equilibrium condition is developed across the boundary, the process of diffusion, the process of diffusion, once we have this, what we call as the equilibrium condition is developed across the junction, and what happens at this stage is that the number of electrons crossing the boundary will be equal in two directions. And the electrostatic potential difference across the p-n junction at this stage is known as contact potential when we have an equilibrium, or we call it barrier field, or we call it junction barrier. So the region in which the region in which the potential changes from positive to negative is called a transition region, or is called as simply depletion region. Now, within this depletion layer, there are no electrons. There are no electrons, and there are no holes within this depletion layer who can contribute to the current. So, if we apply an external voltage to produce some reverse bias across this p-n junction. So, if this is p, I'll give it negative, and I'll give positive. If this is p, I have to give it positive, and to the n, I have to reverse bias it. So to the p, I will give the positive, and to n, I will give the negative. So reverse bias. Now, what happens now when we apply this external voltage to produce a reverse bias across this p-n junction? The p end is connected to the negative, oh no, and the n end to the positive. Yeah, it has to be reverse biased. So here we will have negative, and here I will have positive. Okay, so negative will attract the holes, and positive will attract the electrons. So this is the condition of reverse biasing. So what happens is that the thickness of this depletion layer, it will certainly increase when we are reverse biasing it. Its thickness will increase on reverse biasing the polarity of this p-n junction. And the depletion layer now, this p-n junction should be suitably doped. The doping should have been perfect, and there should be a good percentage of thickness that we can think of in this depletion layer. So what happens is that this depletion layer that we have here, it behaves like ionization chamber. It behaves like ionization chamber. When an ionizing radiation or a charged particle passes through this depletion layer, what happens is there is production of electron and hole pair. And this electron hole pair are produced, and these new electrons and holes are attracted towards the ends of the crystal, where they produce a measurable voltage. And this is how we are able to detect the radiation using a semiconductor radiation counters. Now, if we take an example of a diffused junction detector, diffused junction detector. Now, what we have in this case, we have a silicon base, and this is p-type, and then what we do is we have a depletion layer, and then, okay, let me have a depletion layer, and then we have a n-type layer. So this is n-type layer, and it is plated with gold, so that have a proper metal contact. It's gold, and this is depletion layer. So let us mark this as depletion layer. Depletion layer. So what we will have is we have to give the polarity, and then what we will have is so this will be my so from here I will take a connection, and here we will have to register what we have obtained. Now, what we see here is that in this type of detector, what we have is a thin layer. We have a thin layer of n-type material. It's formed on the surface of the p-type material, and the crystal is chosen as silicon or germanium crystal. Now, by allowing a donor impurity like phosphorus to diffuse into one face of the crystal at a fairly high temperature, the contact is made with N silicon layer by a thin evaporated film of gold. And in order to minimize the current flowing in the detector, when no radiation is falling on it, and there should be no current, flowing through it, unless any radiation is being bombarded on it. And And what else is done, that this is why we make sure that this PN junction is reverse biased. So reverse bias is applied to this PN junction. And ordinarily the depletion layer contains almost no charge carriers. So this depletion layer, it does not contain any kind of charge carriers of either of the signs, either electrons or holes. Now, now when so we have to make it reverse biased. So here we must give negative to the p type, and positive should be given to the n type. Okay, that's the case. So here we can have an output. Now, when an energetic charged particle travels through this depletion layer, what happens is its interaction with the crystal produce electron hole pairs. Okay, so they produce electron hole pairs, and electrons and holes are swept away because there is electric field available there. So what happens to the electrons and holes? They are swept away by the applied electric field and are registered as a voltage pulse across this external resistor R. And this way the presence of the charged particle can be detected using this diffused junction detector. Now these detectors have advantages. I mean, the number of charge pairs produced in the semiconductor material, if you look here, so it's approximately 10 times as large as that of number of ion pairs that are produced in gas ion chambers. So here electron hole productions are very large in comparison to the ion pairs that are produced in a gas chamber. And the energy expended per ion pair in a gas is nearly it's nearly 35 electron volts. And if we compare it with the semiconductor detectors, the energy that will be utilized is of the order of 3.5 electron volts in case of silicon. So the pulse voltage that we have is therefore 10 times higher. Thus, we can say that the detector has much better energy resolution than other radiation type of detectors, preferably ionization-based detectors.